one moment. Something did not work right. Oh, maybe I have to pick sources. Can you hit
Yeah.
OK?
Okay.
Yeah.
Done.
Yes, VGA.
Yeah.
Press OK.
Press.
Yeah.
So they remove the.
Oh no, is it really HDMI? Because.
They remove,
Yeah, I know, thanks.
Sorry.
Relax the stand up and do it. Do you have HDMI?
But it's VGA to HDMI, you know? Oh man.
Oh my god, is that?
But it doesn't look like it's
Read the instruction.
Can you check on mine?
No, I think I have an idea what it is. I don't think it's the remote's going to help.
No, you can sit down between it.
What? Hang on, I know what to do.
Really? You wanna give the command?
The resolution might not be 800 by 600. It
But
could be something different.
Is this thing can
High definition.
No, this will make a difference. Hmm?
High definition.
Yeah, maybe it's high def.
Oh.
Maybe. Go on, read the manual then. Think you're so great. Now, high definition. What's that?
Yeah.
Oh, what?
Too small.
Just
Really?
wait, please.
Take some time, Justin, huh?
Now, hang on.
Oh, that's clear. That looks nice.
I wish there was. Sorry, I wish there was a little stand for it or something. Like, oh. Wait a second. Now, here's.
Here's this fan.
Uh,
No, look.
I know what I'm doing.
So yeah, half. On the edge, on the half edge.
Yes. Hold on. I got it. I got it under control. I know what I'm doing. What? No. What are you doing? Down. Yeah, I know that. I need it like here. Whoa.
Do you have something else? Another door?
That will do, won't it? That will do.
Now put this.
It'll do. It'll do.
No.
It will
No,
do.
okay.
It will do.
Too small.
Ah, it's not too small. What are you talking
It's
about?
not.
You need to buy glasses. I've talked to you before about this.
I don't like that.
No, I asked for pity, actually.
But I think it's too small.
Yeah.
Dude, it's not too small. It's
Can't read HP.
there.
I can't see.
But you're not you're supposed to just see what I write, that's all.
But still, there's gonna be and like the written stuff. Typed stuff.
Look, it's there, now. You'll be fine. I promise.
You don't trust your promise, by the way.
You shouldn't. It's wise not to. Ah, it'll do. Look, I haven't played with it enough. I'll figure it out. It's only day one of the new projector.
In the morning, do you know in the morning it goes down? You don't need a
No.
How much for this black project?
What do you think?
200?
I think it was 100. If it was 100, I'd just buy it myself. I think 350. Something like that. All right. Let's have a look.
I need a big screen from World Cup.
Let's have a look at Hooke's law. That's the questions there. I'd be worried about.
Who's in charge of the project?
Not really anyone in charge of them. It's not like there's a projector leader or something. And we need permission. because you're shaking. And it makes it more exciting.
Don't have that your table with that table, we don't want to.
Yeah, that's right. Separate your tables out a bit. Keep going. Keep going. I know. It'll do. It'll do. Alright. Okay. So let's have a look at these. Now, of course, naturally enough, my pen decided not to work right now. There we go. We're back in action. Right. So the first one, did you write it down? It's constant 5, and we want the extension if there's a force of 20. So what's happening here, you have your material, and the constant is K. No, sorry, the constant, what did I say it was? 5. And the force is 20 newtons. So what is the extension? So you have F equals Kx, or minus if you want. The minus is just for the direction, I won't worry about that. 20 equals 5x. Now, are these newtons and per meters? Yeah, so this extends by 4 meters. Whatever the material is, rubber or something like that.
That's what?
That's it, really. You probably didn't even do this.
Me?
Yeah, you. Did you do these last night?
I was absent.
Yeah, okay. 2. What is the spring constant of a spring that's attached to the ceiling and extends by 2 centimeters when 1 kilogram is hung on it? So what you have is your spring here, and there's 1 kilogram on it, so there's a downward force of 1g, and the spring is given back a force of F, which equals Kx. But you know that should equal 1g, because that's the down force, and it should equal the up force. So you have Kx equals 1g, but the x is 2 centimeters. So the K is g divided by 0.02. 490.5 newtons per meter. Get off the phone, Fahad, unless you want trouble. You already missed class this morning. Okay. Did you write that down?
Yeah. 3.
Okay. 3 now. So these are very short questions.
Just stop it up, I just need my answer.
You were busy messing on your phone, so I'm not going back because you were Facebooking someone. Hey, what's up? I'm in physics now. Lol, Stephen doesn't know I'm on my phone. No.
That was fair.
What?
One that was fair.
Right. No,
I was reporting your channel actually.
you were not. You were not. It's like, oh, but I was subscribing to all your videos on YouTube. Really, I was. A spring is placed on the ground, a weight is placed on the spring, and the spring compresses 3 centimeters. How much work is done? No, I didn't say, sorry, I didn't say the force, did I? So I should have said the mass. So we'll make it 2 kilograms for fun. So 2 kilograms. You place it on top and it will compress then. So here it compresses a distance of, how much did I say? 3 centimeters. Now there's a force going down here of 2g, and there's an up force from the spring, and here they're balanced. So you can know that F equals 2g, Kx equals 2g, 0.03 K equals 2g, K equals 2g divided by that. So the K is 654 newtons per meter. But that's not what I want. I want how much work is being done. So what formula is that? It's a half k x squared, isn't it?
Yes.
So if I put the numbers in there, I get 0.2943 joules. Yeah?
Why fine?
Because of me, I'm moving the table and the wires are attached. That's why. Now it's fine. But I said there is another way you could do this one. So if you were to look, well, does anyone actually know another way to calculate the work done? What?
Fx.
Fx.
Half Fx.
No.
Oh, yes.
No.
Okay.
At the beginning, it has a potential energy of m. What's m? Come on, Quran, focus, please. mgh. And the m is 2. This is a 2 kilogram. The g we know, and the height we don't know. I'll call it h. Afterwards, what's its potential energy? Again, it's mgh, but it's not h anymore. It's h minus 0.03 because it shrank by this much. So what's happened to the energy here? The energy has reduced. But energy isn't reduced. So the reduction is just was converted into work. I mean, that's how much work was done, how much energy, potential energy was lost. So the spring has this energy now. The block did work on the spring. So the difference here, to go from here to here, the difference is 0.03 times 2g. Now I really hope it's the same number, otherwise I don't know. No, it's not the same number. Of course not. That'd be too nice. No, actually, I forgot. Yes.
Why 2g? Multiplied by g, you get the same number.
2g multiplied by 0.03.
No, just g.
Why not 2? The 2 is for the m.
Yeah.
Now, actually, I'm sorry, I remember this came up as an issue in one of the exams. So, this number here is equal to 0.5886. Now, what's happened here? Now, you don't need to do it this way. The answer was done when you stopped here. But why is this method not quite the same? What it is, there's something you have to think about. At the beginning, this had potential energy. At the end, well, it's still at rest, so it's still potential energy. But there's some energy now in the spring. This is how much work is being done.
What's the energy in the spring?
We worked it out as this number. At the beginning, it's 0 joules of energy in the spring. It's not compressed. And later, it's 0.5886 joules. So as the spring is being compressed, that is when the work is being done. Okay? So as I'm compressing the spring, that is when the work is being done. So it's wrong. It's wrong to say this is how much energy is in the spring, but it's wrong to think about maybe this as being the work, because this is only at the end after you put all the energy into it. Really, in other words, the work is the average of these two. If you add these together and divide by 2, you get this number here. Because I suppose this is the start, this is the end, and this process here of compressing it is the work. Anyways, I was hoping that would work out nicely, but it was a bit more complicated. And now I'm glad that I actually did it, because I remember this came up in the exam. So what am I trying to say? Yeah, point of the story is you should use this formula and not potential energy, because potential energy things get a little bit messy. I think the reason, right, let me give you the reason here for another complicating reason here. Do you remember this formula here? F work is force by distance.
Yeah.
That formula only works if the force being applied is constant. If the force is being changed, what do you think is happening? What do you do differently with the formula? So let's imagine at the beginning the force is F1 and at the end the force is F2. So maybe this is a person pushing something and it moves a distance d. Well, the work is not Fd because the force is changing, isn't it? So what do you think you use instead? Well, you don't use F, but you use F1 plus F2 over 2d. This, the average force. This is why my formula didn't quite work out here. I had to use the average work because the force is changing. It's like I have to use the average force. So this sometimes happens in the exam, very rarely, and there's always a way to do the question where you don't have to take averages. Okay, so it's just something to be mindful of. Alright, the last one. 4 people sit in a car, each of mass 65 kilograms. Sorry, because I moved it. Don't drop it. Wait, hang on, maybe the remote.
You can take this in your pocket after it.
Yeah. Whoa! Whoa! Careful, dude. Don't touch it, yeah. That'll do. I'm starting to feel like maybe the bigger one wasn't such a bad idea.
No, maybe you should put it. No, it's gonna be that small.
Yeah. Anyways, the last one. 4 people, each of mass 65 kilograms, sit in a car. The car reduces in height a distance of 1.5 centimeters, and the car is 2,000 kilograms. So you can think about it like this. Here is my car of 2,000 kilograms, and then there's 4 springs, and then you have your 4 people, and their mass is 65 times 4. And what happens is that the car height drops 1.5 centimeters, is that right? Yeah. And then when the people get out of the car bobs up and down slightly. So, do you remember the formula for t? 2 pi square root m over k.
Yes.
Now we don't know the k, we have to work it out. But when everybody is in the car and the springs are compressed, you know that the weight must equal the force by the spring. So you know that F must equal W. How many springs are there though? 4. 4. So you know that 4kx must equal the weight. So you know that 4k 0.015 must equal the weight, which would be 2,000 plus 65 times 4. So that's 2260g. So you can get the k here.
2.260.
2260. 2260 divided by 4 divided by that. So the K is huge, which is normal for a car. 37,667 newtons per meter. So you got a huge K, but the spring in a car is quite stiff. It's very difficult to compress the suspension, the shock absorbers. They're very difficult, you know, they're not like normal springs.
But in the new car.
I guess so, true, yeah.
What's the document?
Is there a question?
The W.
Is the weight of the car and the people in it.
So that
Are you sure?
Yeah, it's 2,000
plus.
plus 65 times 4.
Okay, there's 4 people.
That's what I said, isn't it? Yeah.
Okay.
Okay?
Okay, so now I'd like.
Now they get out of the car and the car starts to bob up and down. So the
How?
time, huh? What do you mean how? When you get out of the car, you know the car wobbles a bit.
I just saw a second now.
Yeah, well that's what, I'm calculating the time. So you already know that the answer should be in the order of 1 second. So we have 2 pi. Now what do I use for the m?
2000?
Which is the mass.
Yeah, what do I use?
The car.
Yeah, see, there's lots of masses here. Which mass do I use?
The mass of the car.
What is the mass?
So the passengers get out of the car.
What do we think?
What is the mass of that?
It is the mass of the car,
Yeah.
because the passengers are out now. So it is 2000 over 37667. So you got T is 1.4 seconds about. So the 4 people get out of the car wobbles for about 1.4 seconds before coming back to its original position. The springs are so stiff and damped that the car very quickly stops wobbling after 1 oscillation. So what really happens here, if you were to look at the graph, here is the position of the, here's the time, and here is the position of the spring. So when people are in the car, the spring is flat, the same length, right? And then what happens when people get out of the car? Does the spring length increase or decrease?
The spring length.
Increases. So when people get out of the car, it increases,
Yeah.
and then it wobbles back down, and then it comes back to rest though at a higher value because the spring has kind of decompressed.
Not the high, the normal like.
The normal.
The normal, yeah, which is higher. Well, I mean, it's higher than when the people were in the car.
Yeah, of course.
So this time we're estimating as about 1.4 seconds.
Okay.
A reasonable number
Yeah.
for 4 people getting out of the car.
Yeah.
Believable. We are happy with this. Alright, so
Can you go above?
yeah, sorry, you want the calculations here. So the stiffer the spring, the bigger the K. So for cars and machines, you're looking at 30, 40, 50,000 newtons per meter. Yeah? Okay, can I close this, KJ?
Yeah, sure.
KJ?
Yeah.
Right, so we'll do the last materials section here.